Welcome to Hot Chips 2023. Session 4, CPU 2.
Don holds 52 patents and has been the lead architect for a variety of Xeon and obviously Itanium processors. In addition, he has an extensive background in RTL design, validation, and post-silicon debug. He lives in Colorado. I was just speaking with him, a big outdoors fan. He loves hiking and bagging 14,000er peaks, so you should ask him about that. Of course, skiing, fishing, cycling, snowboarding, and photography. He has 4 kids, 5 grandkids, a grandson on the way, and most importantly, a fierce rescue cat. Please welcome Don.
Thank you, Rav. Good afternoon. Everybody ready for things to start heating up? Might already be hot. So I am thrilled, really, to be on stage today to talk about my favorite processor I've ever worked on, Sierra Forest. It's our newest Xeon processor powered by our efficiency cores. I'll use the term E-core several times. I'd like to acknowledge Stephen Robinson, who is our efficiency core chief architect, for his contributions not only to the slide, but to the processor I have right here in my hand. So you'll recognize my first slide. Chris Gianos earlier showed the same thing. On one hand, there's nothing that's really new or There's nothing really new or different here. This has been a scenario that's been in play for quite some time. We have a range of workload types that we configure our processors to meet. On the bottom right, those workloads are task parallel in nature and benefit the most from a lot of cores and basically high performance throughput computing. These two attributes, as Chris mentioned, are the basic starting point when a end customer looks at choosing which processor configuration they would like to deploy for their workload. And as we move up on the per core performance, we're fundamentally reducing the core count, adding power per core, gives us frequency per core, probably cache per core, additional memory bandwidth per core. And there are a number of workloads that a lot of people have talked to about today that benefit from a task being accomplished in a specific amount of time. We often refer to that as an SLA, or service level agreement. What we see over time is we are moving our processors up and to the right to improve the performance of this entire range of workloads. Moreover, this breadth of workloads is growing over time. It's important to know, Amin referred to TCO earlier today, which is great because I don't have to explain it too much, but we do use that term, total cost of ownership, in the terms of capital expenditures and operating expenses to understand how do we make our processors better. We don't look at just performance. He was basically speaking my language. It's important that we deliver the best performance per watt at any particular core performance. So these workloads do need to make a trade-off. Or would they prefer more cores working on many tasks, or do they really need a core? It's multiple cores in reality, but needing to complete that task in a certain time limit, and there's a range of workloads in between that our final end customer really wants to utilize for our processor configs. In the past, this range of hardware configs was fundamentally controlled by core count. Throughput processors had the highest core count, and as we reduce core count, we move up and to the left. The TCO math basically points us towards adding as many cores as we possibly can at the proper per core performance and the proper per core bandwidth from memory and I/O to deliver the best possible solution. As Chris talked about earlier, we have the opportunity to continue to focus. We've never lost this focus on our performance core, to focus on performance per core workloads. You can see this spans quite the range, basically the upper portion of our performance per core chart. And also, we want to address any dense data parallel workloads with that core. We introduced our E-core product, Sierra Forest, to really improve, substantially improve the core density, which will improve the TCO, and the performance per watt for those throughput workloads that are task parallel in nature. As Chris mentioned earlier, to really provide even more value to our customers, they can build one platform. We can plug in a Granite Rapids to that platform, boot and run software. We can take Sierra Forest, plug it into the same platform, run the same software, same firmware, same platform. Only one platform needs to be run. What happens is these two processors run the same software, but they have differing power performance profiles. This adventure of performance per watt, power efficient performance, starts fundamentally at our core microarchitecture, which has been and continues to be laser focused on power efficient performance. It optimized every aspect of the microarchitecture to deliver that. In addition, for Sierra Forest, this core has to be capable of deploying in data centers at scale. So we will include a number of our important Xeon advanced features. If we dive into the core, looking at the front-end control, we have a fairly large cache, 64 kilobytes, which is going to provide more hits for modern workloads whose code footprint is growing. While their code footprint is growing, it's important for our branch prediction to become better for those large dynamic code footprints. In addition, we need to extract parallelism at the very beginning of the process here, so we are able to deliver 6 instructions per cycle to the rest of the machine. For energy efficiency reasons, there are 2 by 3 decoders. Each of these by 3 decoders is lower latency and lower energy than a full 6 wide. As we move into the execution control, we'll find that parallelism is the theme. We provide parallelism with 5 wide allocation, 8 wide retirement. We discover this parallelism with a 256 entry out of order window. And we execute that data parallelism with 17 execution ports. As we move into the core execution system, the 17 ports provide two significant values. One is to address a wide breadth of workloads, scalar workloads, vector workloads, integer workloads, floating point workloads, mixtures of everything. In addition, and this is, I found very interesting, each of those ports basically becomes more energy efficient because they focus on a very narrow set of operations. So we activate the fewest transistors possible to perform that operation. You'll hear me say over and over, everything we do is for performance and power efficiency. As we move into the memory subsystem, it was really important that we provide symmetric read and write bandwidth. So we have dual store pipelines as well as, in addition to dual load pipelines. We have 4 megabytes of L2 cache. They are shared amongst either 2 or 4 of these cores. To manage a lot of outstanding misses, we have a 64-entry buffer. This is able to support feeding or decreasing the exposed latency of a lot of these misses via the advanced prefetchers. With these 4 cores sharing an L2, users can use Intel's Resource Director technology to help control the quality of service of those 4 cores sharing that instruction and data. And as I mentioned, we also have added our advanced Xeon features. Data error detection and correction is extremely important. It starts down at the lowest level. Our L1 data cache has full ECC support. We have data poisoning support, machine check support that can be recoverable if the software understands what has happened, as well as local machine checks, so we are containing any errors to the minimum context in which they occurred. The Sierra Forest core also supports a full 52-bit physical address. You'll find that that comes in key to actually hold the key IDs for something we call TDX, which I'll get to in a little bit. Performance is important. Power efficiency is important. Security is always important. So I wanted to say a few words about that. We've added a couple of additional security technology. One is control flow enforcement, which helps protect attacks on the return stack buffer. There's also a virtualization technology for endpoints, which helps protect attacks on the TLB with a hypervisor. To further ensure that the processors are secure, the team has come up with an innovative speculative execution validation methodology, which helps quite a bit to expose any possible attack surfaces. In addition to the security features, we also want to highlight some of our advanced vector instruction capabilities. With wide vector capability, of course, we want to fuse, multiply, accumulate to increase the number of floating point operations per cycle. And we have specific instructions to enhance inference code, as we see inferences becoming more prevalent in most workloads. So now we take these cores. We assemble them into what we refer to as a core module. That core module contains 2 or 4 cores connected to a 4 megabyte L2. That L2 has an interface to the mesh, as well as the last level cache slice at the bottom has a full cache agent and home agent pipeline that's also connected to the mesh. This diagram looks very similar to what Chris showed you for the P-core. Conceptually, we remove the P-core and replace it with an E-core module. Everything outside of that are the same IP, and you'll see in a bit that we reuse the exact same silicon as well. These cores are single-threaded, and I want to make sure that folks remember that this last level cache is shared among all cores. There's one last level cache domain per socket. We take that core tile, as we refer to it, and set an array of them into our compute chiplet. In a Sierra Forest package, there are 3 chiplets, 2 I/O die and 1 compute chiplet. As Chris talked about, that complex connected via EMIB technology creates one monolithic mesh. We have I/O tile in the north I/O die. The south I/O die is the exact same silicon. There's just basically 2 instances where we rotate it by 180 and plug it into the bottom. We support PCIe Gen 5, CXL 2.0 with Type 1, Type 2, and Type 3 devices. We have our UPI coherency links. We have our integrated accelerators for encryption, decryption, compression, data streaming. All of those are common capabilities, the exact same die that are used in Granite Rapids. That provides a lot of commonality at the system level and also at the software level that leverages these 2 processors so they don't really seem different. Our compute die is set up as an array of cache and core slices. Fundamentally, the left cache slices are addresses associated with the left memory controllers, as well as the right with the right. We support our trusted domain execution, which isolates VM guests from each other via encryption. The entire design is focused on power efficient throughput performance, operating task parallel sort of workloads at their best. So we support up to 288 cores in a 2-socket node. And on this power efficient theme, although we have TDPs above 205 watts, we start at 205 watts because that is an interesting 1U power efficient configuration. This is the so what Soltis slide. The so what here is at the data center, a rack of servers, Sierra Forest servers, can provide 2.5 times as many vCPUs, virtual CPUs, threads, as a Sapphire Rapids CPU. This is accomplished because of core density and by power efficiency. The bottom right graph is the one thing, if you walk out of here with anything, this is the one thing that I want you to think about is, I'm often asked, quite often, when do I use a P-core product like Granite Rapids and when do I use an E-core product? And I start with the first question, how much core performance do you need per core performance, per thread performance? If you want more, then we'll start with your P-core product. Second question would be, what kind of accelerators, instruction accelerators do you need? We may, dense data parallel, you may lean more towards our P-core product. But you can see how clearly our focus on Sierra Forest in this throughput range provides even additional performance per watt, which is on the x-axis, over Granite Rapids, which is providing substantial performance per watt improvement over Sapphire Rapids. Now notice that both of these are also moving up in the performance per thread category. This relates back to the very first slide I showed, that Chris showed as well, because these are two important key attributes that customers look at when they're deciding what configuration of the processor do I want to deploy. Now these shapes are oval in nature because they represent not just one CPU, but actually the range of configurations we offer, from the higher core count, higher throughput CPUs, to the lower core count, higher per core performance CPUs. That's true even in the Sierra Forest bubble, where the higher core count, higher throughput are off to the right, and the lower core count, where we have 2 cores per module to increase the performance per core, cache per core, memory bandwidth per core, improves that performance per core. So I think I've demonstrated that we set out to do what we wanted to do with our Sierra Forest processor. Is we really were able to take this efficiency core focused on throughput performance, energy efficient performance, and turn it into a processor product that delivers on key customer values, improves their TCO fundamentally. You heard about the OpEx, which are operating expenses, and CapEx, the capital expenditures. Having more cores and better power efficiency in a socket improves both of those. Our E-core program is augmenting our Granite Rapids P-core product. They're not competing. They have some overlap, which is intended, but there's a clear focus of intended workloads for each of those. Of course, we want to be able to support some AI inference workloads. We do support FP16, bfloat16, and int8 inferencing datums. As I've mentioned many times, our focus was on throughput, density, and efficiency. And we need to do that across this range, broad range of workloads and deployments, and make sure that we can deploy at scale. I think what I've demonstrated is we do have a highly scalable architecture that does address our throughput efficiency and provide value to our customers for the next decade of compute. With that, thank you for your attention. I really appreciate it.
Thank you for the great presentation, Don. Really appreciate it. Great talk. Thank you. We have time for questions. I saw there was actually quite a few questions coming in on Slack. Maybe we'll start with that, Alisa or Deepak.
Certainly, Ralph. So there were some questions about whether this E-core supports any extensions like the AMX extensions or the AVX features.
Okay. So Sierra Forest does not support the AMX instruction set. Dense data parallel, those are workloads we focus on our P-core. Nor does it support AVX512 ISA, also dense data parallel focused on our P-core product.
Charlie, go ahead. Charlie?
Yeah, is the 1 slice and the 2 slice version socket compatible?
When
Like
you're saying
one
slice-
core die and 2 core die.
Oh, if you're referring to whether the 2 core per module or 4 core per module,
Or two core chiplet module and 1 core chiplet module.
they're completely platform compatible. Can't tell the difference. The lid covers all of those details. Yes.
Thanks.
It changes the power performance profile of the workload to increase the performance per core.
Take a question on the left.
George Hosmer from Chips and Cheese. So you just said that you don't support AMX or AVX512, but do you support AVX10 or 10.1 on Sierra Forest?
We do not. We're not able to intercept AVX10 instructions, which are fundamentally AVX512 instructions. The main change there is we're exposing the capabilities in CPU ID differently. So it's simpler for software to look at the CPU ID and say, does this processor support AVX512 or let's say AVX10 or not? What's the width? We'll run this code. Otherwise, we're going to run this code.
Thank you.
So Lisa, do you have another question?
I've got questions. So give me a second here. Some sharp eyes out in the audience noticed, I'm going to reference Andrew Krapavin from Rutgers, that your 3 megabyte LLC appeared physically larger than the 4 megabyte in the picture in your diagram, your 4 megabyte L2 cache, and physically it looked like the 3 megabyte LLC was larger. I don't know if that's just the way you drew the diagram, or is there some feature in that LLC cache that makes it actually take up more diagram state?
Okay, so if I understand the question, my PowerPoint picture seems to make it appear that a 3 megabyte cache takes up more area than a 4 megabyte cache. I shan't answer that question. It does not necessarily. That is just my cartoon representation.
Okay, thank you.
Yeah, go ahead, please.
Pradeep from KLA. From a software compatibility perspective, assuming I'm not using any AMX or AVX512, can the software compiled for Granite Rapids run on the Sierra Forest without changing? And is there any advantage to recompiling it and rerunning? Will I get any throughput advantage if so?
Right. So, for the most part, yes. To not be able to run a program compiled on Granite Rapids on Sierra Forest, you have to use compiler flags that say add AVX512, add AMX. If that's what you want, then you want to run on a performance core product like Granite Rapids. We build up a lot of our libraries, and the official Intel mechanism here is for software, look at the CPU ID, identify what capabilities this processor has, use those capabilities. So I think I answered your
So
question.
yes. Thank you.
Okay, this is another one from Slack. Chester Lamb from Chips and Cheese asked, since the cores within a module are sharing a voltage and frequency domain, does that mean the cores in the module can't be independently, dynamic voltage modified? Or are we misinterpreting?
Don't understand that question. So this is not unlike every Xeon processor we've built since J-Town. Has a shared last level cache. All of the cores have their own private L2. In our case on Sierra Forest, the 4 cores share the L2, but all of the cores in the system share that last level cache. I think I just repeated what I've said before because I'm not sure.
It was more of a question of whether these 4 cores can be independently clocked, if you can change the frequency and or voltage of the cores independently, or are they 4 cores that are sharing the cache locked together?
I'm sorry, I heard cache, I apologize. So I did have in that one slide that this 4-core module, including the L2, are all on the same clock and voltage domain. And the L2 is the interface to the mesh.
Okay, so they act in lockstep.
Yes.
Yep.
Take one last question from Ian, and then we have to kind of move on.
Sorry, Ian from Aldermore. This sounds like a silly question, and I mean it in a very silly way. If a customer were to conceptually request one of these chips with built-in HBM, as Intel has already provided other Xeons with HBM inside, would that potentially be possible with the architecture as it stands today?
Ian has a big customer waiting for you.
Sorry, I didn't know that.
My comment was Ian has a big customer waiting for you, Don.
I can't speculate that we've no announcements on any. What I heard was an HBM.
Yes, conceptually, could the architecture support
I
it?
can't comment on any future
That's why I
speculative
said
things we're going to
conceptually.
do.
That's why I said conceptually.
Okay, thank you, Ian. Thank you, Don. Thank you for your time. Really appreciate it.
Appreciate it.
Thank you. Next up is a talk by AMD on a client SoC, the AMD Ryzen 7040 series mobile processor, presented by Mahesh, Subramony, and David Kramer. Mahesh is Senior Fellow Client Architect of the SoC client line. He's architected multiple Ryzen processors, including all the way back to the first generation Threadripper-based product line, and the 3000 and 4000 series in between, the desktop processors. Since 2003, he's been with AMD in architecture and design in SoC, spanning mobile, desktop, and server, so he's really covered the range. David Kramer is a fellow client architect at AMD, and he's a primary SoC architect for the current Ryzen processor series since 2020. David has always been inspired by and pursued disruptive technologies throughout his 20-plus year career, including architecture leadership roles at Freescale, Compaq, Agere, IBM, and he's also worked at 2 biomedical-based startup companies that you can ask him about as well. So please welcome Mahesh and David.
Hello, everyone. It's an incredible honor to represent the talented and dedicated design teams at AMD that have made the AMD Ryzen 7040 series processor possible. Now, the design teams at AMD had a very clear set of goals when they sat down to decide the next generation of mobile SoCs. To a first order, it was just doubling down on the attributes that made the prior generation, the 6800 series of the Rembrandt SoC, successful. So increased compute in the form of the next generation CPU and GPU architectures, improved performance efficiency expressed as performance per watt or performance per area, and improved power efficiency were key goals that ranked highest at the order of relevance. But in addition, we were keen to invest in new drivers of pervasive technology that we believe will benefit our customers in a big way in the coming years. The modern PC, with its acute focus on performance efficiency, is fast reaching an inflection point where domain-specific accelerators are almost as relevant as general-purpose compute. So with the Ryzen 7040 series of mobile processors, or the Phoenix SoC, we've tried to strike the right balance between traditional compute and specialized accelerators, combined with an intelligent power management framework and an efficient memory and I/O subsystem to deliver an SoC that we believe will meet the needs of the modern-day ultra-thin mobile PC user. From a compute standpoint, the Phoenix SoC is anchored by the latest Zen and RDNA architectures. The Zen 4 high performance and efficient x86 core delivers a 13% higher IPC, or instructions per cycle, over the prior generation, and the RDNA 3 graphics builds on the performance efficiency of its predecessor and adds even more improved performance per watt per compute unit. The Phoenix SoC introduces the first integrated AI engine on an x86 processor. So this dedicated AI engine is able to perform certain tasks independently, thus freeing up the traditional compute for other tasks. So we believe that this will provide power efficiencies to certain use cases and user experiences that will become table stakes for mainstream and ultra-thin mobile premium PCs going forward. From a technology standpoint, higher transistor densities with the TSMC N4P and upgrades to majority of the accelerators, including video, encode, decode, display, and audio, further the power efficiency of the design by accelerating race to idle. This in turn adds as a tailwind to the battery life of these SoCs, which is a key factor for a mobile user. So we believe with the right components and in the right proportions, we believe we have a tailored compute for every client use case that keeps coming up in this space. Let's take a quick look at the high-level block diagram of the Phoenix SoC. At the heart of the SoC is the 8-core Zen 4 CCX or core complex. Each of these cores can run in single-threaded or multi-threaded mode or 2T mode for a total of 16 threads. Each core has a 1 MB private L2 for a total of 8 MB of L2 in the design. And these 8 cores share a 16 MB last level cache or L3, which is populated by the victimizations of the L2 and carry both clean and dirty lines. So in short, a 8-core, 16-thread, 1 MB of L2 per core, 16 MB L3 CCX that's connected to the Infinity Data Fabric with a 32 bytes per cycle port for both reads and writes. Looking at the graphics engine, the RDNA 3 engine consists of a single SC shader engine, dual SA or shader array, with each SA comprising of 3 WGPs or workgroup processors and 2 render backends on RB pluses. Each WGP has 2 compute units or CUs for a total of 12 CUs that have a 2 MB of GL2 cache in the design. So in short, a 1 SE, 2 SA, 6 WGP, 4 RB plus 2 MB GL2 graphics engine that is connected to the Infinity Data Fabric through 4 32 bytes per cycle data ports that handle the increased bandwidth requirements that come with this graphics engine. The third compute pillar is the XDNA engine, that is a 4x5 mesh of AIE DSP process with memory tiles that orchestrate memory traffic between these DSPs. This is also connected to the data fabric through a 32 byte per cycle data port for maximum bandwidth into the design. The display controller has 4 display pipes that support 4 simultaneous displays independently. The system management unit is a cluster of microcontrollers that control key operations within the design like security, power management, sensor fusion, I/O control, and core processor frequency control. The SoC also carries all the high-speed I/O that's required of an ultra-thin mobile PC with 20 lanes of PCIe Gen 4, controlled by 2 independent PCIe controllers, and a USB subsystem that comprises of USB 4, USB 3 Type-C, Type-A, and USB 2 ports for a total of 8 USB ports. The memory subsystem consists of 4 UMCs or Unified Memory Controllers, which each control a 32-bit PHY or channel for a total of 128 bits of memory. The UMCs can address both LPDDR5 and DDR5 devices for a max transfer rate of 7500 megatranspers per second or 5600 megatranspers per second respectively. And the UMCs also support AMD Memory Guard or TS Semi Transparent Secure Memory Encryption. Rounding out the SoC is connecting all of these IPs to the memory subsystem is the next generation Infinity Fabric that has improvements in QoS or quality of service, arbitration logic, as well as bandwidth improvements, including a system probe filter that is designed to help reduce probe traffic in the design. Area is a key constraint for almost all SoCs, and the level of importance for that is escalated in mobile SoCs given the prime focus on power efficiency. With the help of the TSMC N4 15-layer metal stack, we're able to drive incredible density increases in our design. And this allows us to add all the relevant features and all the performance that we would have wanted to add into the design while staying within the budget or the bounding blocks of the design like power, area, cost, and package fit. As you can see in the die shot behind me, we managed to squeeze in nearly 2x the number of transistors in the die as compared to its predecessor, or the 6800 Rembrandt SoC. And we were able to do this with a 15% smaller die footprint. This allows us to put this SoC in the same package, a 25 by 35 package, as well as the same platform infrastructure that enables us to deliver higher performance while staying within that same envelope. So let's take a quick look at that performance that this SoC delivers. From the IPC that is delivered by the Zen cores, and the focus on driving higher Fmax at Vmax, higher frequency at max voltage, through a combination of clocking, thermal, and power management algorithms, we're able to achieve a 16% single-threaded performance improvement over the prior generation. The single-threaded performance is a direct reflection of the responsiveness of a system, which is, again, a very important metric for the mobile PC user. The core team's singular focus on driving performance efficiency, really helping both server and client SoCs, helped drive stricter targets for both leakage and CAC, or dynamic power, which enables us to be able to get a higher effective frequency within a given power envelope. This drives that higher frequency along with that IPC improvement that the cores bring. With SMT, this drives a 25% higher multi-threaded performance compared to its prior generation. Improved performance efficiencies within the graphics engine, as well as rest of chip power reductions that help drive a larger budget for the graphics engine to operate in, allows us to drive a 22% higher graphics performance for an ISO configuration comparison. In other words, a 6W versus a 6W comparison compared to the prior generation. And all of this, along with rest of chip power improvements and key accelerators in the design, help drive higher performance in applications like in productivity, and drive a larger battery life and active power efficiency. Taking a quick look at the core architecture, and I'm not going to go into too much detail because this was covered in a prior session. Just recapping, the Zen 4 architecture brings significant improvements to the fetch engine, with improvements in branch prediction, as well as a larger op cache and larger bandwidth for both fetch and decode. Implementation, increases in the rest of the engine include increases in buffer sizes, including the larger register file, deeper buffers throughout the core, and load store improvements. In addition, the Zen 4 design delivers a power-efficient AVX512 support in the floating point unit. In addition, we also doubled the L2 cache from a 512K per core to a 1 MB L2 per core. So all of these additions, including improvements in the design for lower latency, help drive higher throughput, and this delivers the higher IPC that we had seen in the previous slides. So this higher IPC, combined with the multi-CPU multi-threaded efficiencies that the design drives in a single homogeneous 8-core complex with a large L3, allows for uncomplicated OS scheduling, which leads to unfettered application performance. This is evidenced by the double-digit performance increases that you see in application performance over a wide variety of benchmarks with a comparable competitor. Taking a quick look at the graphics architecture, significant PD improvements and a focus on improved power efficiency per compute unit helped drive the GPU max frequency to 2.8 gigahertz for the Ryzen 9 product, and up to 700 megahertz, up to 2.6 gigahertz in the Ryzen 5 products, which is a 700 megahertz improvement compared to its prior generation. The 12 CUs, each capable of 256 FP16 operations per cycle, running at 2.8 gigahertz, contribute to the 8.6 peak teraflops, which is a 25% higher peak throughput than the prior generation. This, along with the massive bandwidth increase that the LPDDR5 and the DDR5 systems bring compared to the prior generation, and the power efficiency in the rest of chip that I mentioned previously, helps drive a leadership in or best-in-class iGPU performance for this mobile device. Now, gaming in a TDP constrained environment or a thermally design point constrained environment, whether it's for a mobile device or a handheld device, is gaining significance or relevance in the recent past, and the performance requirements in that form factor is not getting any lower. We believe that the Ryzen 7040 series is an excellent choice for gaming in that constrained environment, and it's evidenced by this significant performance advantage it enjoys over a comparable competitor. This is 1080p games across a varied set of games measured as frames per second or FPS. So in the first half of the talk, we introduced the Phoenix SoC, went through briefly the pillars of the traditional compute that it enjoys, the goals it's setting out to achieve in terms of performance efficiency and power efficiency, and a quick competitive comparison in those major pillars. Now for the second half, I'd like to invite my colleague David Kramer, who's going to walk us through those domain-specific accelerators and other technological improvements we have added into the design to make this a best-in-class SoC. David?
Thank you, Mahesh. We'll take over from here. Again, happy to be here. Thanks for letting me host this part of the session. So diving right in. So again, Ryzen AI featuring our XDNA technology, first time in an x86 processor. Let me take you back a little bit in time. This is beginning of 2021. We're in the middle of executing on the Ryzen 7040. And this is, by the way, this is pre-ChatGPT, this is pre all the hype around AI. We'd seen some interesting CNN results, vision results, and so we knew there was some potential here. But we also knew, as we saw in the Zen 4 processor presentation, hey, we have VNNI instructions in the core. We have deep learning operations in our graphics. Do we have this covered? Or should we go after, integrating a more optimized inference engine into the SoC? And since I'm presenting this here today, I think you know how the decision went. And now I think in 2023, we see this as really the transformative technology of the modern generation, right? It's very rare you kind of see something like this come along that can really change the way we, the way we work, the way we interact with each other. And we're pretty much all in on this. So let's dive a little bit into the architecture itself. It's built out of a stallic array of compute tiles. We call these the AIE engine tiles. At its heart is the AIE core. This is a VLIW SIMD engine. Again, data and instruction parallelism. It's tightly coupled to a data memory and an instruction memory. It has its own DMA engine and an interface to the stream, basically a stream interface. The stream interface is a grid-style interconnect that connects all the tiles together. It's again high bandwidth, low latency, and carries the added benefit of a multi-gas broadcast capability. As you heard earlier, that's actually very beneficial in distributing weights to all the engines. Down at the bottom here, you'll see what we call layer 2 SRAM and global DMAs. These are staging RAMs for intermediate activations and weights. As you know, this is very much a data flow architecture, so all the operations are done based on the data coming into the engine. So our DMA engines basically stage that up so that the processor operates at the most efficient mode. We connect it directly to our Infinity Fabric, as Mahesh showed you, for high bandwidth access to our main system memory. By its design, it is programmable, right? Because of that, we can implement models that we know of today, as well as models that maybe we don't know of yet today. So, CNNs, LSTMs, and now obviously the transformer-based LLMs are all candidates for this accelerator. You'll see here we focus this again on energy efficiency, so we tend to prefer the lower precision operations. And from our research, most of the applications we're looking here, actually are friendly to Int8 kinds of performance. And if you can get Int4 as well, then you can see that you can get another 2x improvement there. The F16 hangs around. There's some operators or layers that may not be friendly to Int8, so we still carry that behavior going forward. Another very interesting feature of this IP block is it can be spatially partitioned, right? So I can take it and have it as one monolithic unit, or I can make it as 4 individual streams. So 2 benefits to that. The one we talk about here is more AI responsiveness, because I can run these things in parallel. But the other, I think, real interesting feature this adds is the ability to give applications a piece of the IPU. And they actually think they own essentially an IPU, and there's no worry about interference between other applications trying to use the engine, because we've really spatially partitioned it. You know, it came up earlier, we do support 50% weight sparsity. So if you got a properly designed and sparse network, which I think is the way to really scale this in the future, right? You get the benefit of reduced bandwidth, reduced power, and reduced compute. And a lot of these networks are very friendly to sparsity. And of course, we always, you know, go out of our way to put, you know, fine-grained clock grading into all of our IP blocks, and this is no exception. Okay, so we can build the fanciest hardware engine in the world. If you don't have an end-to-end software story, it's really useless, right? So kind of looking at our view of the world here, this is the vision. It'll take, you know, time to realize. But if you look at the top here, this is where the model developers live, right? If you're a data scientist and you're developing your own models, or if you're like me and you're not that smart, so you have to go to, you know, a Model Z or a Hugging Face and find something that kind of closely represents what you want. Basically, you take that into these, you know, well-known and well-used frameworks, TensorFlow, PyTorch. You train it, you tune it, right? You get it to where your error and your accuracy is where you want it, and now you're done as a model developer. And now you're ready for model deployment, and that's where our software stack comes into play. And our vision is pretty simple, right? We want a common set of APIs. We want a common set of libraries. We want a common set of compilers and tools, right? Model compilation, model quantization, model pruning. And then basically when we get down to the runtime, we'll plug in the execution provider of choice for the hardware accelerator that you want to target. So in the case of the XDNA, that's the Vitis AI. In the case of the core, that's ZenDNN. In the case of CDNA, that's ROCm, right? DirectML in the case of RDNA. And, you know, we're kind of uniquely positioned. We offer solutions from the cloud all the way to the edge, right? And I think this software story says you build a model once, you can target any of our platforms. Is, you know, I think it rounds out that story quite nicely, and definitely a focus of us to make sure that everybody can take advantage of the hardware we're putting in these devices. So, okay, so what can you do with such an engine? Well, we partnered with Microsoft, and we ported 3 of their studio effects to the IPU. You'll see the 3 there on the right. I don't know if you're familiar with these. Eye gaze correction is basically a detection algorithm finds the eye and a pupil, and it redirects it to the camera, because it's very annoying when you're talking to somebody, it looks like they're looking off in space. So it's kind of meant to be more of an engaging video conferencing experience. The blur, I'm sure everybody's familiar with blur. Basically a segmentation algorithm, detect the person from the background. But what we've seen is this pixel level accuracy of this algorithm is much better than the CV counterparts that we used to use for edge detection, because you're basically training the model on what a human face looks like. So it's very good at getting that proper separation between the foreground and the background. And of course, the auto framing that's a face detect with a crop and zoom. It's a pretty neat effect. It basically looks like the camera's following you around as you move around the field of view. And in fact, the camera is, of course, all stationary in the laptop. Other ones that may be even more exciting coming down, sensor AI-based personal assistants. We're looking at a lot of graphics enhancements that are based on AI. You all know about upscaling probably, but there's also denoising, there's stylistic effects, a lot of interesting applications of graphics. And then, of course, the holy grail, the content creation, right? The ability to use LLMs, the AI assistant to basically create this presentation for me. If I had this technology, I could have told it, hey, go build me this presentation, and I could have, taken a vacation. And then a variety of automatic speech recognition, speech to text, translation, so on and so forth. Ryzen AI does this with, real-time performance power. I talked about the security, and certainly cost is better than a discrete solution, or even arguably in the cloud. Pivot real quick, this is SoC. Every time we build a new APU, we focus a lot on both active and standby mode power, right? Because after all, these are battery life devices. I see a lot of laptops here that are probably on battery life. So maximizing that is a priority for us. Don't have time to go through all these, but I'll talk about a few that were important. The deep Z8 state, this is a hardware managed state that can take very brief periods of idleness, right? Even between keystrokes, right? It has enough time to basically get into this combination power gated and clock gated state and wake up in a time that's imperceptible to the user. That's why it's, hardware managed and video playback or other examples where we get high resonancy in this state. I talked about the AI inference engine. The other thing I'll mention, we put power gate on this as well. That's generally activated when we're not using it. DVFS on our PHY, our DDR PHY, USB PHYs, we carry generation to generation. We noticed that there was a lot of improvements that could be had on a USB 2 PHY that we've had for years and years and years. NVMe has a lot of built-in power management techniques. We just, software wasn't taking advantage of them. So we took another swap at that and said, we can go off and do that. Now I'll just talk about this last one, scenario detection. We spent a lot of time analyzing battery life workloads, and video conferencing was one of them. And we figured out sort of the right settings for our platform to make this both a user experience and the maximum power efficiency. So that's why we claim our battery life on video conferencing is quite good. Shifting to the Infinity Fabric, this is our coherent interconnect and accelerators and our processors to our memory. It is a coherent fabric. It's used across pretty much all of our portfolio, but in terms of client requirements, right? We want a better power efficiency. We leverage the process technology. Mahesh talked about that already. We study all the workloads and we categorize them into, compute, IO bound, video conferencing, gaming, and we basically create these operational modes that say, oh, in this mode, I'm actually going to operate at this state, which is the most power efficient for that application. Similarly, low power retention. So if we're in a partially active scenario or a lightweight active scenario, the Infinity Fabric could go into its own low power states and wake up in microseconds of time. And of course, linearity, matching the bandwidth to the dynamic power consumed was another priority for us. And one speed bump in both the DDR and the LPDDRX frequency. I won't spend a lot of time on this. Pre-pandemic, we thought of the video codec. It's a very specialized accelerator. We thought of it mostly as a decode engine. You're consuming content. Now with video conferencing, now we see encode as important. So we have a new AV1 encoder in here. We put a dramatic speed up on this engine. The speed up allows it to race to idle. It's an engine that benefits from a race to idle scheme. And it also, with this performance you'll see here, it can do multiple streams in parallel, probably more than you'll ever need. But video conferencing, when you're doing a 3x3 or 4x4, you're actually decoding multiple streams in parallel. And having the performance of this engine matches that quite nicely. We have an audio coprocessor on chip. We also see this as an area of AI innovation. We added a second DSP, a little more SRAM, and some low power clocking modes for cases where it's in a standby and it's the wake source. Low power audio playback, speaker and headphones, it's used for that. Also, this is where an AI noise algorithm could also run, if you can fit it in the footprint of these DSPs. And then a couple of wake on audio features. I'll talk about ultrasound detection on the next one, but also keyword spotting. You say keyword, wake up, right? And you can basically bring the laptop out of its standby mode without having to touch the computer, So ultrasound presence detect, we do open up this engine called the ultrasound engine to our third parties who have this kind of fusion presence detection technology. Kind of the way it works is you send out a tone above 20 kilohertz of outside the human audible range, below 32 kilohertz, so it passes the bandpass filter of the speakers and mic. And basically, when there's a large object in front, in the field of view, if you will, it gets a Doppler shift, right? So you can apply deep learning techniques or just normal Doppler technology, and you can, if you're good, you can then distinguish a human from a curtain moving or something else. This connects through a third-party ultrasound audio device or auto module interface and allows an audio human presence detection mechanism. One of the benefits of this is obviously privacy. People don't like the camera always running, as well as the lower power of this is, since it's in our SiFive domain and on, you don't have to run the x86s to do this. Mahesh went through most of the I/O connectivity. I'll just touch on it. USB 4 on our USB-Cs, 20 lanes of Gen 4, talked about the memory. We carry forward our AMD FreeSync, which is the ability to synchronize our graphics to a panel that has a variable refresh rate. If the panel has its own buffer, it can do its own self-refresh update, so we don't have to wake up or make our DCN actually do that work. Selective update, it says there's a region that only change from frame to frame, so we have to send that region up. It's this technology we've had for a while, as long with DisplayPort 2.0 and HDMI 2.1. One upgrade for 4K cameras, we did move to USB 3 for our camera interface, and that is our secure BIO port for things like Windows Hello. So in summary, with this device, we're bringing, I think, our latest and greatest technology in our portfolio. Mahesh talked about the Zen 4 cores, 5.1 gigahertz. It's our latest graphics, our RDNA 3 technology, our brand new XDNA technology that we just introduced today, all in a 15 to 30 watt TDP envelope, which we think makes this, as I said on the top, a best-in-class ultra-thin mobile processor. So while I click through this, I do want to thank our AMD global team. This, the execution on this processor wasn't without its challenges, but we, the team really around this, they delivered it, and we're very proud of what the team has done. So with that, let me invite Mahesh back up so we can field some questions.
Thank you, David. Thank you, David. Thank you, Mahesh. We have time for questions. I saw there were several good technical questions out in Slack, so perhaps Elisa will start with those.
So this was one of the more popular ones. Raghav Gupta from UC Berkeley entered it. He was asking, how is the 50% weight sparsity supported? Is it similar to NVIDIA's tensor cores, requiring exactly 2 to 4 sparsity? But the more general question, how is the weight sparsity done?
Right, so weight sparsity basically says if you properly design your networks that you have contiguous chunks of zeros, we don't necessarily need to do that operation. We don't even load it into the memory. So when it comes out, there's no point in multiplying a 0 by a constant because we know what the output's going to be. It's going to be a 0. So if you structure that sparsity in a way that we can take advantage of it, we don't need to do that operation at all.
Yeah, I think that question was, how do you detect that sparsity so that you don't have to do anything?
That's during model development. You design that in.
Okay.
Go for one more question, Elisa.
Certainly. There was a question about the Pluton processor for your security. Is that implemented as a separate tile? Is it a separate die in your SoC?
It is. This is on? It is. Yeah, it is implemented as a hardened IP that we get from a microcontroller standpoint, and it runs the Pluton firmware on it. We believe that is something we work closely with Microsoft to deliver the right security solution for our Windows users.
Kevin, go ahead.
Hi, Kevin Creel, Terrace Research. My question is about the Ryzen AI IP block. Now, when you started the design work, this is, I think, before AMD had announced they were going to acquire Xilinx, but that's a Xilinx block. So what was the thought process to choose that block from Xilinx to incorporate into your SoC?
Right. So you're right. So at the time, the acquisition wasn't completed. But we did take a look around, and we didn't have this technology at AMD. So we looked at what other players had. We found what Xilinx had with this Xeon technology. It was pretty mature. It was almost, I would say, off the shelf. It was pretty close to off the shelf. We could integrate it fairly rapidly. So what we did is we entered into a licensing agreement to license that technology, and that's when we decided we're going to pull it in.
And just to follow up, are you planning to integrate all your different software stacks? You've got Vitis for the Ryzen AI. You've got the Rockham for the GPU. Go with CPU. Is it a more integrated package in the future?
I think there'll always be sort of the hardware specific pieces that'll be unique, but we kind of want to go above that and say, okay, from a user perspective, from a model development, from an API perspective, let's keep it as consistent as possible. And that way it facilitates the ease of migrating your model across our different devices.
Yeah, thanks.
Yeah, go ahead on the left over here.
George Kozman from Chips and Cheese. Sort of a follow-on to that last question. Will you be supporting ROCm on the iGPU?
ROCm on the iGPU.
Yes. On all RDNA is the statement. So
Yes.
I think that will be how we would go forward with the support. Yeah, that's.
And a second quick question. Why didn't you guys add a second Infinity Fabric link to the CPU cluster? Because you only have one, and that does seem to be looking around a bit of a memory bottleneck.
Second Infinity Fabric? No, this is.
It's like a second port, because you only have one 32-byte port to the.
That's correct. The current core complex is connected to the fabric with a single 32-byte data port.
And sort of the question is, why didn't you add a second one?
Why didn't we add a second one? Oh, we believe that it's a combination of both area, power, and performance. Right? For the benchmarks that we care about, they're not. From a CPU bandwidth standpoint, we don't believe that is necessary. Right? If you, from a server standpoint, I think Ravi talked about GMI wide, where we widen that interface. I mean, that is something we look at in that space, and maybe even in extreme desktop.
Okay, thank you.
Hi, Chester Lamb, also from Chips and Cheese. I've heard that on your desktop RDNA3 products, you actually have a decoupled front-end clock where the work distribution can run at a different frequency from the shader array. Is that also done on the iGPU here, as it is also based on RDNA3?
I don't think. Can you repeat the question?
Yeah, I didn't
So say on desktop RDNA3 products, for example, the 7900 XTX, you can run the front end at 3 gigahertz and the shader array at 2.8 gigahertz, for example. The clocks are decoupled. Are they similarly decoupled on the multi-pod?
Well, the integrated RDNA3 architecture inherits all of the features from the discrete implementation of the design. But I don't think we have found significant use cases for running them independently. But yeah, we would retain the same capability. It's the same design that's been cut down with a smaller configuration to go into the iGPU, work as an iGPU.
I also have a kind of silly question. So you mentioned that you were using ultrasound and the Doppler effect to detect users.
I think we need to go on. We're running short on time.
Okay, let's head off then.
Let's catch it off.
David will be out here. We can definitely have a conversation over drinks later. Thank you, Mahesh. I'd like to introduce the last talk in this session. It's by SiFive on the new P80 high-performance RISC-V processor. And this has been quite a session in terms of the caliber of presenters we've had. It's been all architects, the key architects from the representative companies. The last speaker, Brad Burgess, fits in that row as well. Brad is a fellow at SiFive. He's actually had quite the lengthy career. He architected the 6 generations of ARM-based CPUs that Samsung has been bringing out. He's worked at AMD, where he was a senior fellow and chief CPU architect for the Bobcat and Cat families, notably. And before then, he was at Motorola, where he was the chief architect for several generations of PowerPC, including the ones that went into the original iMac, as well as the ones that are roaming around on Mars still. So please welcome Brad.
Good afternoon, and I'll try to get us back on schedule because I gather I'm the only one between y'all and refreshments coming up. So, one thing kind of interesting about this industry, it's never boring. It changes dramatically. One of the first projects I worked on was a PowerPC part under an IBM license, and then I went to AMD and did several parts under an Intel license, and more recently I was at Samsung doing a number of parts under an ARM license. And for me, RISC-V is kind of interesting because it's the first open standard I've really had a chance to work on. I think my looking at it, given the support of the open software community, the upstream pushes that are going in that are really supporting this architecture, all the people that are getting lined up to make products behind this, I think it's going to be interesting to see how this plays out as far as perhaps an inflection point in the industry. So anyway, we'll see how this goes, but I'm excited about it myself. First of all, let me go a little further here. Again, just as a brief kind of intro to RISC-V in general, it is based on standards. It's referred to as a open standard hardware assay architecture. Anybody can build it that wants to. It's not effectively licensed with a bunch of caveats behind it. There's at least 2 options here. There's the microcontroller profile that's defined, and it's fairly lightweight, but it gives you a lot of flexibility to do what you think of in the microcontroller space. For example, it really doesn't define a supervisor space, but it gives you those flexibilities to do a lot of things. Also, we have an application processor standard that's where you really get into these higher performance machines. This is a standard that's defined for modern OSs, modern applications, virtual machine, the whole 9 yards. We also have, as far as product IOMMUs, WorldGuards defined, interrupt architectures, debug and trace, the components that you would think you would need to really go flesh out a full system. Again, a couple other comments here. RISC-V is somewhat open from the standpoint you can build accelerators and still maintain software compatibility to a degree. You still can support the full application space, and then it still has space to do some interesting application-specific things as well. Just to give you a little history, our first out-of-order machine was the P550. It was shortly after followed on by the P650 and a smaller version, the P450, for power mix and match kind of optimizations. Those 2 designs also had sister products where we added an out-of-order vector unit. That's the 670, 470. And you can also see the standards that they support. And here I'm going to talk about 2 parts in particular, the P870, which is our 3rd generation out-of-order core, and the P870A, which I think is interesting from a standpoint of for automotive-specific applications, and we've added some features into the design for that in particular. Just seems like this is a standard slide. It's been on about half the slides today, so forgive me, but you know, the model we're doing here fundamentally is put together a mix of cores into a cluster. They can be 650s, 670s, 870s, 470s. You can mix and match all kinds of cores. You can even drop in some of our intelligence cores in here if you wanted to within a cluster. The model we have is we have a shared L2 in this cluster for various reasons, for improving some performance. Again, we'll go into a little more detail in later slides, but we also have multi-cluster interconnect. We have shared L3 caches. We have memory ports, IO coherent ports that are part of our fabric. We have advanced interrupt controllers that support full virtual machine, so the interrupt controller can be knowledgeable of a virtual machine that's an idle, as an example. We have the full debug and trace features that you would want. We have full VM translated, nested paging IOMMUs. And we also have a feature called WorldGuard security, which is, it's a way of partitioning and isolating for security. And I think it's somewhat unique for what we're doing, but it does, I think, give us an advantage. We've learned some lessons from what other people have done, and I think it's a good solution for where we're heading. Just briefly to go over the pipeline, and we have what I refer to as a zero bubble predictor. Some may also refer to that as a smart next line predictor. We have an iCache. We have a Tage-based branch predictor, an 8-table based machine. And we have a third stage, which is where our indirect branch predictor comes into play. We have decode, rename, dispatch, issue, as you might imagine, register read, execute writebacks. As you can see here, we support a 4-cycle load latency. We have 2 and 4 latency floating point instructions. And then we have our vector instructions, which can run anywhere from a single cycle out to 8 cycles, and in some instances longer than that for some long latency kind of permute situations. But in general, a fairly clean pipeline, and I think to a great extent this is what RISC-V allows us to do. And this is, again, in some ways not a pipeline diagram, but more or less an instruction flow diagram. And I'm going to just walk through these pieces and give you a flavor for what the machine's actually got under the hood. 64K iCache, 4-way. We do 32-byte fills each cycle. It's got a 1K next line predictor, 64-entry return address stack, a 2-kiloentry Tage direction predictor or conditional branch predictor, depending on what terms you like. 2.5K entry indirect branch predictor. We do 36-byte fills. That's not a typo. That's a 36-byte fill. And have a 32-entry ITLB at the front end, and that's what keeps the front end busy as far as translation, and that seems to be fine for the workloads that we're considering. 6-wide decode. We handle both 32 and 16-bit instructions. We have a very efficient kind of compressed instruction set that gives us some code density advantages. Also, we have a number of fusion cases that we can also handle within the decoder. For, some people may argue, well, why doesn't RISC-V have more complex memory addressing modes, as an example? The philosophy, which I think is an interesting one, is to take those instructions that you would build that up with and fuse them, as opposed to just eating up all your opcode space. So we have a number of fusion cases that we handle in the decoder. Register renames, 228 on the integer side, 240 on the floating point side, 128 vector renames. Rob can handle up to 1,120 instructions, and that is the extreme end of it. It's not typical, but the way we do some Rob optimizations, you could actually have that many out-of-order instructions in flight. 6-wide dispatch, feeding a number of units. Through the vector sequencer. Oops, let's get one here. The vector unit. This is a full out-of-order vector unit. It's got 32 entry issue queue on the front end. 228 mainly symmetric vector execution pipelines. You can see the difference with divides and masks and permutes. Dual crypto units. One thing I'll point out is up the top end of the queue there's a vector sequencer. The RISC-V ISA has a unique version of what they call LMUL, where you can have one instruction basically operate on a concatenated block of registers. And so what we do here is we fracture that up into micro instructions and let micro instructions pass on down the pipe. It frees up decode bandwidth, but still gives us the full out of order nature of things. Go a little further. Floating point, we have 48 entry floating point issue queues, or basically 40. It's a pair of 24 entry floating point issue queues. Mostly symmetric floating point pipelines except for divide and squirt. We have 2-cycle FAD, 2-cycle FMUL, and a 4-cycle MAC. And it can handle single or double for those latencies. Integer unit, across the board there, 96 entries. It's really 16 entry issue queues times 6 there. You can see a division of ALUs, multiplies. We have 2 of those. We have a single divide unit. We also have one unit that's both branch and ALU. If you're going to spend the money for register ports, might as well use it most efficiently. And so it can handle both class. And then we also have a single branch only unit, which is also used for the indirect branches and handling those scenarios. In case you're curious, I think our branch mispredict penalty can be as low as 9 cycles. So that's kind of interesting with some of our competitors. Load store unit, 64K data pipe, or data cache, 4-way. 1 load pipe, 2 load store pipes, which seems to be typical for this class machine. 32 load entry queues. They happen to be unified the way we handle them within our load store unit. It lets us keep track of history and whatnot a little more easily. 48 load buffers, 48 store buffers, a 64 entry DTLB, and beyond that we have a 1K entry L2 TLB that is also shared with the front end. We do have some fairly advanced stride and pattern matching prefetchers, primarily in the L1, and we also have mechanisms to broadcast and pull into the L2 as well. Our L2 cache is non-inclusive. We have snoop tags out in the L2 cache to cover the core. That really is an interesting trade-off. It allows us to not necessarily have to just pollute our L2 with what effectively is redundant data in the L1s. At the same time, it's non-inclusive, but it's not exclusive. There are scenarios for like instruction sharing and whatnot where we can allow it to keep redundant copies as is useful. For what it's worth, 32 bytes per cycle in and out. That's a load and store per cycle, so it's full duplex. And it's the same protocol between the L2 and the L3. The L2 and the L3 both. They're configurable as far as the amount of banking, as far as the size. So you have a lot of flexibility as to how you want to put your system together. And we'll talk about that here next. You know, again, as I mentioned earlier, the model here is around a cluster topology. And one of the advantages over a cluster topology is we have an L1 that goes straight to a very large shared L2. We're talking about 16 cycle latency into our L2, so it's not bad by any stretch. But it also gives you some opportunity to do data sharing between cores that you really can't do if you push that latency very far out. You know, again, the snoop latencies are very responsive. The example here, what you'll see in the upper right, that's a 4-core cluster as an example with a 4 meg L2, and you can see the 4 banks highlighted there, plus the interconnect fabric is also in there. If you want to compare areas, you see the load store unit, integer unit, floating point vector. You see the units kind of broken out in the color table. On the left, you see kind of a typical example of how we connect this together. You build up a cluster, you tie it together with the tie link to interconnect fabric. In this example, we have L3 slices around the periphery. There are interesting trade-offs, and we have the flexibility to whether those L3 slices are on the periphery or whether they're distributed throughout the system. And there are different trade-offs there depending on your tag directory lookup as far as how far away your cluster is and how far away your memory port is. And so this gives us a lot of flexibility to play around and optimize the system for what the application really wants to do. And again, this example, you got 4 memory core ports, you got I/O ports, and that's an example of what you'd see for a larger topology. For a consumer topology, here's an example of 2 P870s sharing probably a fairly large L2 for depending on the market you're going into. 4 470s, which are the smaller of the cores, sharing again an L2. Both core clusters sharing an L3, and so you have all kinds of optimizations with regard to powering down, whether it be clusters or cores. And then we also have a very efficient E6, which is an in-order core. As part of, in this example, is part of the always-on arena or block. Again, you can get interrupt controllers, debug and trace controllers, IO menus, WorldGuard gadgets. If you want a true real-time random number generator, we have those as well. So, I mean, we believe we have the whole shop that you need to put together a full SoC. This, again, a little more detail on the plans for our automotive version of P870. Automotive is a different beast compared with most of what we think about, because in the automotive space, it's all about fault detection, functional safety, reliability. And so what we have here is the variant specifically for automotive. It has extensive error checking, error injection, error reporting, and error recovery features that aren't necessarily in the base 870 product, and you just want to buy it that way. But to give you an example, all the register files have parity. The caches are ECC, both tag and data coverage. Almost any large block within the CPU has some form of error detection, including the execution pipes. Going further, what you'll see is the L2 and the L3 have high reliability cache controllers. The arrays themselves are ECC protected, but the controllers themselves have fault detection and redundancy built into them, so that if your L2 controller should hiccup, you know it, and you can detect those faults and report them and do something with them. The interconnect fabric, again, has been built more robust, supporting additional error detection and error handling. Other system components, such as the interrupt controller, they as well have been beefed up to give us a high reliability scenario here. As such, a single A70 core will meet the ASIL B requirements, and then we can run 2 cores in lockstep, and again, we have the infrastructure to support that to our customers, which gives them the full ASIL D requirement as well. Together, you wrap the CPUs up with the enhancements that are done there, the enhancements that have been done for the infrastructure, the interconnects, and all the I/O device peripherals going with this. The system is designed to meet the future requirements of the automotive market. And just, it's interesting. This isn't our first rodeo. We have a pretty broad portfolio of products here. We have, on the left, you see an automotive selection of products. We have an intelligent series of products that are designed for AI/ML using very wide vectors. We have our performance series that are primarily out-of-order cores, including the 800 series there. On top of that, we also have Essential series. This is our more in-order, very power efficient, very small cores. And again, with the whole plethora of components here, you can build up a system, you can mix and match components, and you can do a lot of things which we don't believe are necessarily easy for some of our competitors to go do. Lastly, and again, this is a bit of a teaser, but in the next couple of months, you'll be hearing about our Napa class core, which is, again, our 4th generation out of order. We're starting to do various pieces of work on it, and it give you some flavor for what the future holds for us. And with that, I'll be very short and open up for questions and go from there.
Great job.
That's back on schedule.
Yeah, very good. Yeah, Don gets us back on schedule. Absolutely. We have time for questions. Alisa, I saw again a few good questions on Slack.
There are a couple of good questions here. This is more of a clarification question, it feels like, from Christoph Novak from Moore's Law is Dead. He asks, is the cluster always formed from 4 cores? It seems not from one of your slides, so.
You can build a 1-core, 2-core, 4-core. We've got a lot of flexibility in how SiFive's methodology is one on giving us flexibility in design. And so, no, it's not 4-core only. You can even configure your L2 depending on how many slices you want, or how many banks you want effectively, depending on how many cores you have. And so there's a lot of trade-offs that we can make that give us an opportunity to go through a lot of different product design options.
Well, thank you.
George, go first.
George Kramer from Chips and Cheese. So, 2 questions. First, you said that your RB can hold 1120 instructions, but how many entries is there actually? Is it 280?
Oh, shoot. Without going on to all the options and doing the division in my head, the bottom line is we have the ability to bundle groups of instructions as part of our ROB entries, and we have a lot of ROB entries. It's well over 200, so do the math, I guess.
280.
And your other question? Sorry.
And my other question, real quick, what version of RVV are you supporting? Is it 1.0 or is it 0.7.1 or is it 2.0?
RVA is going to be 23.
No, RVV specifically. So what version of the vector instructions are you supporting? Because RVV has not been ratified yet. It's been frozen but not ratified.
And yes, and RVA 23 hasn't been ratified yet either. It's a proposal. I'm trying to remember exactly which one ended up in 23.
Chris is sitting up front. He knows. He can answer.
Which is in 23?
Which one is it?
1.0.
Thank you.
You want to just repeat the answer?
Yeah, the 1.0 was ratified a long time ago. The 1.1 is what this one is. And it includes, I believe, things like B-float and what have you.
We'll go with Kevin.
Kevin?
Hey, Kevin Kramer, Theories Research again. For the automotive part, when you do lockstep, because it's an out-of-order core, how do you guarantee that everything follows the same path? Do you have is there data or connections between the 2 cores that guarantee that they execute in parallel at exactly the same rate, or do you disable some features that make it more static?
No, I mean, if you look at designs nowadays in general, just to be able to test them, there's not a randomness in a core. Yeah. From reset going forward, a core is going to do what it's going to do based upon the inputs coming in. So when you lockstep the 2 of them, they both get identical inputs coming in, usually with a time dilation, and then you can compare, and there's not a arbitrary nature to it.
Even in the branch predictors and all that, that's all.
All the branch predictors behave the same way. I mean, the only thing that wouldn't behave that way is the random number generator, and we don't put that in the core.
All right, thanks. So, Alisa, maybe another question?
Yeah, so there was a question about if you have any estimated clock frequencies for this part, for the P870.
This isn't a product announcement. That'll come out here in the next month or so. We're going to be competitive. You can say that. Well into 3 gig range.
I'm going to let you say that.
Okay, I'll say that.
Thank you very much for great talk. I'm Yasuo Ishii from 10th Trend. I have a question about the performance number. When you evaluate the performance, what L2, L3 configuration are you using? Basically, as you mentioned, the L2, L3 has a great configuration, I think. Mm-hmm. So I want to know how large L2 cache, L3 cache are you using for projecting the performance?
I believe the performance that was shown up there is for a 4 meg L2 and I believe a 16 megabyte L3.
Yeah. Sorry. If you can share, can I ask you the DRAM latency as well? The L3 miss latency.
I'm sorry, I didn't understand. Can you repeat the question, please?
If you miss in L3, obviously the AT is going to access to DRAM to get the data. How long DRAM latency are you using to evaluate the performance?
I'd have to go back and look. I believe it's LPDDR5.
Oh, yeah. Yeah, thank you very much.
We'll leave it here.
Okay, thank you.
Thank you, Brad. Really appreciate it.